All right, let's kill these dinosaurs already. Our last section of the Mesozoic is called the Cretaceous Paleogene Extinction. It's abbreviated KP because the Cretaceous is abbreviated K because Carboniferous is the abbreviation for C in the geologic timescale. As another naming convention, a lot of times you'll see this called the KT extinction, and that is just an older scientific reference. The geologic timescale has changed over time, and the time period that is now known as the Paleogene used to be part of a time period known as the Tertiary. The Tertiary has been eliminated from the geologic timescale. You might notice that the Quaternary is still on the geologic timescale. I feel like that is slated for extinction as well. There is a group of people who revise the geologic timescale in kind of a regular way, and so more modern conversations about this extinction call it the KP extinction, just for clarity. And it involves the extinction of most dinosaurs, but not birds. Ammonites, which again were super common during the late Cretaceous. And there you have a nice picture of one. The only remaining coiled shell cephalopod that exists today is the nautilus. And there are some other smaller organisms, lots of foraminifera went extinct, but they're not nearly as exciting as the dinosaur extinction. There are a couple hypotheses. One is much more widely accepted than this other, but let's start with this first one, which certainly did not make life any easier for dinosaurs during the late Cretaceous period. So the first hypothesis has to do with the supervolcanic eruption, and this is the eruption of the large igneous province that's known in India as the Deccan Traps eruption. The Deccan Traps eruption was a mantle plume that reached the surface right before, during, and then just after the dinosaur extinction. So the dinosaur extinction itself is dated about 65.5 million years ago, and the Deccan Traps eruption occurred between 66 and 65 million years ago. It was a large outpouring of basaltic lava, resulted in decreased sunlight, toxic water, like to the point where the acidity of rainwater may have prevented dinosaur shells from calcifying properly, but all of those things were contributing factors. The Deccan Traps eruption was incredibly large. Today we can measure lava flows from this eruption with a thickness of over 6,500 feet. So again, more than a mile thick of lava flows covering an area of more than 12,000 cubic kilometers. So a huge environmental perturbation. But the overwhelmingly accepted hypothesis for the KP extinction is an impact of a comet or an asteroid. And you saw that in the video that you watched. Here is the Chicxulub structure on what's known as the Yucatan Peninsula of Mexico. And if we do a cross section through the Chicxulub structure, you can see, first of all, this round structure here with broken up chunks of rock beneath where the main impact would have been. And you can see a very large area of melted rock right at the extinction event. You can see broken up chunks of breccia deposited immediately on top of that melt. And then you can see during what we would now call the Paleogene, but used to be called the Tertiary, just regular, uniform, horizontally deposited limestone deposited on top. So you can see it's a very brief event right at the extinction horizon. So I recently watched this movie called Greenland with Russell Crowe, and it's actually scientifically not awful, I will say. It really it simulates like what would happen if a impact occurred today around the size of the dinosaur extinction, and it really illustrates really well what would occur in terms of a heat blast that would travel in all directions from the impact site, an earthquake. The earthquake at the KP extinction is believed to have been like a magnitude 11, which on the Richter scale, which is unbelievable. That heat blast would have given rise to wildfires, and wind would have carried those wildfires in all directions. This would have been followed by months of darkness because of all of the material that would have been ejected into the atmosphere. A lot of the rocks that fell after impact were molten when they fell back to the earth, and so that would have also contributed to some wildfires. There's lots of cool evidence for this impact, and so that's why geologists find it the most compelling of the hypotheses. So, as you saw in the video, one of the most compelling pieces of evidence is the iridium anomaly recorded in KP extinction horizons. So here is a rock layer section of the KP extinction from Spain. And what you can see is this was a layer that's at the bottom, light colored. It is a late Cretaceous limestone. Marl is sometimes called limestone, is a variety of limestone you just haven't learned about yet. And it's light colored because there's all sorts of happy little foraminifera in here, and their shells are making it light colored. And then here you see the extinction horizon, and there's about 4 millimeters thick of what geologists call an ejecta layer, followed by Paleocene rocks that are dark in color because there are no happy little forams floating around. Well, if we take samples and we match up the location of these samples with their iridium abundances, what we see is something really marked. So this is an iridium plot showing really low background levels of iridium, which is very common, until we hit the extinction horizon right here. And then you can see, boom, this huge but brief impulse isn't the right word, but input of iridium. And then you see basically 2 millimeters here, 2 decimeters here of iridium as it like decays back to background level. So right in the boundary layer, like right in that ejecta horizon, there's over 300 times iridium than we see above or below the event. And again, iridium is associated with extraterrestrial objects. It's also associated in very small amounts with volcanic eruptions, but in much higher levels with extraterrestrial deposits. And we find this iridium anomaly globally. So it isn't something that is small, it is something that is very large. The diameter of the crater in the Yucatan itself is very large, and we can see that material did spread around the globe. We also see something called shocked quartz. Shocked quartz, here's a single grain of quartz that is shown under polarizing light, so it looks kind of psychedelic. But if you ignore the colors and you look at the lines in here, these are fracture patterns in a single grain of sand. And so this single grain of sand has been shattered at the atomic level, and geologists only find those in 2 locations, at impact sites and at nuclear test sites. So you can see that shocked quartz is associated with very small, brief, intense pressures. So we can move along to tektites. Tektites are glass spheres, spherules they're often called, and they're quickly melted rock. These are taken under scanning electron microscope images, and tektites can be anywhere from a couple millimeters to, I don't know, about 10 centimeters or so in length. They are when rocks are rapidly melted, and fly through the air and cool as they're flying through the air, which is how they have this very fluid texture to them. So soot has been found around the globe in end of Cretaceous extinction horizons. So here's another picture of soot under scanning electron microscope. It's the same stuff that you find in your fireplace, really. It's just created by fire. And so it looks like, based on the deposition of soot nearly globally, that the entire globe was on fire that day. Like, I just can't even imagine a magnitude 11 earthquake, followed by a heat blast, followed by worldwide fire. It's just unbelievable what it must have been like. And then around the Gulf of Mexico, we have great examples of tsunami deposits. Tsunamis, we know, are generally created by earthquakes, and so this was a magnitude 11 earthquake, and we can find tsunami deposits around the Gulf of Mexico. So here's where the Chicxulub crater was, and all of these green circles that you see are the location of known tsunami sites that were associated with the Cretaceous Paleogene extinction. It's pretty sweet. And with that, we bring to a resounding close to the Mesozoic, and we begin our search for the age of through the age of mammals in the Cenozoic.